Very warm welcome to everybody here. My name is Los Pagaar. I will be your host for today. And it's my great pleasure to introduce Alice Booth, who will be talking to us about what we are feeding baby planets, chemical inventory of protoplanetary disks as traced by ALMA. Now, a quick reminder of our netiquette. As long as you're in the Zoom room, please use your full name. While Alice is giving her talk, please keep yourself muted. And after the talk, you can always raise your hand for some questions. And when you are asking a question, please show yourself on your video. And then without further ado, I'm going to stop sharing my screen. And Alice, the floor is all yours.
Great. Cool. So thank you for having me here to talk to you today. I'm going to talk to you about protoplanetary disks, which might be a little bit outside of your area of expertise, but I hope, or what your science you're interested in, but I hope that you find it fun. And I'm really happy to have any discussions if you want things clarified or you want to learn a little bit more about any of the things that I discussed today. So my sensible title is The Chemical Inventory of Protoplanetary Disks as Traced by ALMA. And I'm here kind of in the US on the East Coast at the Harvard Smithsonian Center for Astrophysics. But my fun title is really, what are we feeding baby planets? What I'm interested in is how we build planetary systems and what they're made of. And what I do is mostly look for different kinds of molecules that are in the kind of planet formation birth environment. And this is all motivated by the vast array of exoplanets detected beyond our Earth, right? We have different solar systems with different architectures, with different compositions, different sizes of planets, different densities of planets, different elemental makeups. We want to understand all this variety. My approach to this question is to look at the earlier stage, at the birth environment of planets, to try and understand what is the diversity there in these systems and what is the kind of typical chemistry maybe of a protoplanetary disk. So protoplanetary disks form during star formation, so they don't kind of form in isolation. We start with our molecular cloud, which is kind of our time zero. This is cold, dense gas, not very dense, but dense-ish, cold, dense gas, 20 Kelvin. We have dust, we have ices. And at some point, this cloud is going to collapse and we're going to form a young star. So about 10 to the 5 years, we have what we're calling class 0, class 1 protostars. So these are young stars with rotationally supported disks and infalling envelopes. And these are kind of warm, chaotic systems. And as we evolve, we get onto this kind of class 2 disk, which is mostly just a star with a disk. We don't really have much of that envelope material left over. And this is the region that I'm interested in. So what is the makeup of these disks that are about 1 million years old, where we think we might have planets already forming within them? And then this links on to the older, more evolved planetary systems, looking at, say debris disk systems, which are tens of millions of years old, or even fully more evolved exoplanet systems, and also connections to our solar system through the composition of comets and meteorites, and what we can learn about kind of the origins of this material from the disk phase. So here's a nice kind of schematic of a disk. This is where sliced through it, we have our young star, say it's about 1 million years old. The kind of thermal structure of this object is going to be driven by the radiation from the star. So the inner disk is going to be warmer. As we go radially outwards, it's going to cool. So we have radiation from the star will heat the dust, then in turn heats the gas. We also have radiation which will break down molecules. It'll dissociate bonds and more ionized things as well. So this is why it kind of gets colder as you get further out in the disk. So our initial disk is made of mostly gas, about 99% of the mass from our time zero. And most of that is in molecules that we can't actually see. So that is H2, molecular hydrogen, and helium. And the molecules that I look at are more trace species. So simple molecules, elements of carbon, oxygen, nitrogen, and sulfur. And they make up, it's a less than 1% of the total gas that we're able to observe. We also have dust, which is a lot easier to observe. And dust is maybe 1% of our initial mass, and we have a range of grain sizes. So we might start with submicron grains, and over time, these will grow in the disk to at least centimeter sizes, or even more. And on the surfaces of these dust grains, we have ices as well. So we have simple ices, for example, water, ammonia, CO2, but we can also form more complex molecules like formaldehyde or methanol, or even larger, potentially prebiotically relevant molecules on these ice grains. So over time, our disk is going to evolve. Things are going to change. The dust is going to kind of evolve in a large way. It's going to grow. It's going to settle towards the midplane. And some of the dust in the outer disk will drift inwards as well, due to the different pressure felt by the dust and the gas in the disk. And we're hopefully going to build planets. And I think we start with small dust grains and they're going to collide. And hopefully we grow to the cores of giant planets or just small terrestrial planets. And what these are made of is going to depend where they are radially in the disk. So, for example, here I've highlighted the water snow line, which is probably the most important one for planet formation. So planetesimals or comets forming beyond this are going to be rich in water, and then bodies forming within the water snow line are going to be relatively volatile, poor compared to that outer disk. So we have this difference in chemistry radially as we go outwards. And over time, we might form a giant planet, and that's great. Hopefully, we do that in a good number of systems. And what that's going to do is it's going to really change the structure of the gas and the dust significantly. And we're going to build a planet here, and we're also going to form a gap in the disk, in the dust and the gas. And that's going to be observable probably with telescopes like ALMA that I'll talk about today. And in the inner region of the disk, hopefully, we're going to be able to form smaller rocky planets that I think most of you are slightly more interested in. And that should be done, on a few AU scales or less. But these giant planets are going to impact the disk a lot. They're creating a big gap in the gas and the dust. They're creating structures in the disk, and they're going to be accreting directly from the disk gas. So this is a nice way for us to kind of map the composition of this material to what could be the composition of a forming planet. But it might be a little more fun. These planets might be, altering the environment around them. They could be heating material. They could be inducing shocks. It could be a very dynamic and energetic process, and we're trying to figure that out from observations now. So if we want to link disks to planets, I think chemistry is the best way for us to do that. What you're probably most familiar with is the relative abundances of, say, carbon and oxygen. On this top left plot, we have the C/O ratio in a disk. So that's the amount of volatile carbon relative to volatile oxygen in the disk. And as you go radially outwards and you cross snow lines, this dashed solid line here is the gas. As you go radially outwards, you're going to have more oxygen in the gas within the water snow line. When you cross the water snow line, you have more carbon, almost more carbon relative to oxygen. But when you get into the very outer disk, you're going to have at least 1-to-1 carbon oxygen and potentially higher. And that's kind of reflected oppositely in the gas or in the dust or in the solids on the dust. And you can do a similar thing with nitrogen as well. Nitrogen to oxygen is here. It shows slightly different variations across these snow lines. And if you can imagine, if you pull these three elements together, you can create this kind of phase space here, which is kind of exploring, I think, with models, this paper from Pachetti, 2022, where you have different abundances of carbon relative to nitrogen and carbon relative to oxygen, depending on how your planet evolved in the disk. So maybe where it formed and if it migrated and what material was available for it to accrete. With the detection of sulfur or SO2 in exoplanet atmospheres, there's been kind of a more interest in that from the modeling side as well. There's some works that are looking at, say, you have higher abundances of sulfur in your planet if it's forming from pebble accretion rather than planetesimal and gas accretion. This is just one example of a recent paper that's kind of looking into this idea. And finally, you might have planets enriched in metals or very refractory materials, but not in volatiles. And that would tell you that you're creating a lot of refractory or a lot of dust grains and not as much ices. So maybe you're forming within a snow line. I'm not sure. But there are some kind of connections that you can make between what we think is in the disk and what could be in a planet. And there's been some efforts now to try and connect the dots, and that's mostly with observations of very giant gas giant exoplanets and what their elemental makeup is, and trying to infer where they could have formed in a disk. So these are a few examples. I might not have the most recent references for these because it's a little bit outside of my field, but I think that I'm reasonably correct. So what we have here on the left is HR 8799. This is a young A-type star. It has a debris disk, but also at least 4 giant directly imaged planets. We're calling them planets. They're 5 to maybe 15 Jupiter mass objects. And the one I've highlighted here is C, which is kind of about 30 AU orbit away from the host star. And there have been some measurements that have said that the C/O ratio in this disk is about the same as a star, but it has a high amount of carbon and oxygen. So maybe this planet formed via fragmentation of a disk, so forming via gravitational instability rather than core accretion. There is this planet here, WASP-77AB. I think this is in the literature a lot. Every other day I see a paper about this planet. But anyway, in this work specifically, they found very low abundances of carbon and oxygen and more carbon than oxygen. So they're suggesting this planet formed beyond the water snow line and then migrated to its final location. And finally, Beta Pic, which I think is probably one of a lot of people's favorites, has a C/O ratio of they were measuring about 0.4, and they're suggesting that it formed via core accretion, and maybe it was enriched with planetesimals as well. I think it's really hard to make these inferences from a couple of numbers when the error bars that we have on these numbers are still a little model dependent. But I think we need to kind of pin down exactly what's happening in the disk gas and dust and ice to be able to have the best idea of how to map these connections, and that's kind of what I do. So most of my work is looking at disks observationally, and that's with the Atacama Large Submillimeter Array. This is an interferometer located in Chile. It's a picture of ALMA in the snow, which I think is really nice. People think that it's really dry and desert-like up there, but there is snow sometimes, and I think it looks really pretty. And you see all these antennae splayed across this kind of desert. And we kind of use these antennae as one giant telescope to try and look at very small scales at radio wavelengths. So these antennae are quite large. They're 12 meters in diameter, which is pretty big. You can see some people here in this image, and they're kind of moving these around, I think, on these really large trucks, which is pretty cool. I think they have 2 of these trucks, and they move the antenna around a lot, so they change up the array configuration to give us access to different kind of angular sizes on the sky. And this is kind of where ALMA is located on a map, if you're interested. So with ALMA, we can kind of zoom into almost planet-forming, solar system scales. This is an image of the dust in the TW Hydra disk. So this is probably our nearest protoplanetary disk, 55 parsecs away. And you can see if you zoom into this central region, we're looking at rings, so substructures on 1 AU scales. So we can really zoom into kind of solar system scales and think about how much mass is in this inner region of this disk and how could that, evolve into forming planets. And more typically, we're going to get 10 AU scales very easily on objects up to 200 parsecs away, and that's very doable in the dust emission. We're looking at lines, and we can get pretty sensitive with ALMA, so less than a millijansky per kilometer per second if you care about these numbers. And it can really be a lot. It can be a lot better than that. I think we can push ALMA to very high sensitivities to detect very weak lines. And we have a huge range of frequency coverage as well. There's a lot of different correlator options with ALMA, so you can get from almost 30 to almost 1,000 gigahertz, which means you can look at a lot of molecular lines. Although the trickiest thing is probably water due to the atmospheric features that are present. So we've learned from ALMA that disks are very highly structured. This is a gallery of pretty pictures from the D-sharp ALMA large program led by Sean Andrews. And what you see is there are a lot of structures. So this is the thermal emission from the dust. It's about 20 to 30, 40 Kelvin temperatures of this dust. And you see lots of rings of different sizes. You have thinner rings and thicker rings. You have multiple rings. You have some spirals. You have asymmetries. You have slightly smaller, more compact disks. You have some binaries. So there's a whole host of variety of structures. And I'm not going to say that all of these structures are caused by planets, but they could be explained pretty easily by planet-disk interactions under a range of kind of modeling assumptions. But we do think planet formation is underway in quite a lot of these disks. So on the left, we have PDS-70, which is probably the one you know the most. This is the thermal dust emission. And you see this little blob, this little bright spot within the dust cavity is what we kind of call this gap here. The dust cavity, we have this bright blob of emission. And this is probably a dusty circumplanetary disk. So this is a young planet secreting gas and dust from the disk, and it has some dust around it. This is kind of the only most convincing detection of such a thing in the submillimeter wavelength regime. If we go to this middle image here, what we have here is the dust is these 2 rings you can kind of pick out. And these large arms here are the CO gas at a very particular velocity. And there's this little wiggle here, and this can be attributed to, this is kind of a non-Keplerian velocity shift in the disk. And this could be attributed to a giant planet sitting in between these 2 dust rings. Finally, this is a different example of the 169142 disk, which I'll talk about a little bit at the end of this talk. You see there are 2 bright rings here of dust. And then this inlay in the center shows this little bright blob. And this is a point source that was detected in scattered light with the VLT. And this emission could be attributed to a young forming planet. So we're pretty sure that planet formation is underway in quite a lot of these nearby, at least the most massive systems that we're seeing. And what we're sensitive down to right now is really gas giant planets. So Jupiter mass, a few Jupiter mass and up sizes of planets really. So we know that these disks are also chemically pretty rich. This is a nice gallery of images from the ALMA large program maps led by Karen Oberg. So on the left, we have this nice thermal dust emission of this disk with these rings. On the right, you have all the different molecular faces of this object. So we have a lot of different molecules. We have simple carbon molecules, so CO. We have cyanides, HCN, hydrocarbon radicals, C2H. We have some deuterated molecules, some larger chained carbons with nitrogen, some almost complex organics with the methyl cyanide, formaldehyde, more deuterated molecules. There's a whole host of things, a little bit of sulfur with the CS. And you can see that these all look a little bit different. They're all tracing different kind of regions of the disk due to disk chemistry. And you also see some rings and some substructures, and some of these can be mapped to the dust structures, and some of them can. So it's a pretty complicated picture. And I'd say we've surveyed a good number of disks to the level of detail where we can say that most of the time we're looking at disk gas that has a lot more carbon than oxygen. So we see very bright C2H and CS towards a lot of disks, and that's telling us that on tens of AU scales, what we can trace with ALMA, what we're seeing is really carbon rich. So it's kind of this outer disk gas. We see a lot of the CS, but we don't see simple oxygen-bearing sulfur molecules too often, like SO. Most of the complex organics we're seeing are these long-chain hydrocarbons or cyanides, and it's not quite the kind of cometary kind of complex organics that we'd want to find, or like those that you see towards protostars, like methanol, CH3OH. So I think there's a lot to do in terms of trying to detect a lot of different molecules, but it might be that we need to think about how the disk structure impacts the disk chemistry, and if we're observing the right types of disks to be able to find all the molecules we're interested in. So we detected about 30 molecules in disks so far, which is about an order of magnitude lower than kind of what has been detected generally in the interstellar medium. And that's partly due to the fact that disks are pretty small in the sky. They're a few arc seconds at most, and the emission from them is just a little bit weak. They're small objects. They're harder to observe from the ground. So this table is colored basically in terms of the elements in these molecules. So everything, this green is just carbon and hydrogen. The blues are carbon and oxygen and hydrogen. Purple has nitrogen, and orange has sulfur. So for all of these molecules, we also have isotopes of quite a lot of them. Not everything, but the simple stuff, we detect a lot of isotopes of carbon-13, oxygen-18, oxygen-17, some nitrogen-15, deuterium, of course, and a few things, and also different isotopes of sulfur as well, most recently. And everything bold here was detected with submillimeter wavelengths for the first time, so that's kind of what ALMA can probe, but also telescopes like the IRAM 30 meter or NOEMA or the SMA. But everything underlined was seen with ALMA for the first time. And you can see notably that that is all the large molecules. These have weaker rotational lines, they're not as abundant, and we can only access the really big molecules with the telescope, such like ALMA. So what we see with our observation of ALMA kind of depends on the disk physics and the disk chemistry, right? So we have our host star, heats the disk radially outwards, it injects radiation, which generates radicals. We have chemistry. And what we see with ALMA is kind of the cool gas on tens of AU scales most of the time. This has a carbon-oxygen ratio of, say, 0.8 to maybe 1 or even 2. And what we see are these molecules with mostly carbon and a little bit of oxygen, and molecules like CO, HCO+, but predominantly carbon-rich gas. The inner disk is kind of where all the fun is happening, I would say, in terms of we've sublimated all of the ices beyond the water snow line, and we can actually see the kind of full volatile content of the disk. And this is kind of unfortunate that the full reservoir is typically hidden with ALMA in the ices because we're just looking at the gas. And ALMA is really great because you can look at very kind of high frequency resolution observations. So you can really look at very individual spectral lines. It makes it very easy to identify molecules. But it's unfortunate that a lot of the molecules we care about in terms of, say, water or complex organics or maybe some sulfur, it seems to be typically hidden in the ices in a lot of these disks we've observed so far. But as I mentioned, disks have a lot of substructures, so it might be that there are some disks better than others for detecting certain molecules. And for example, these are transition disks. So these are all disks which have these large central cavities, so they kind of have an inner clearing of dust and gas. And I'm not saying that they all host planets, but here's PDS-70 here highlighted, and this is one where we do have potentially 2 gas giant planets orbiting, at 20 to 30 AU in a disk. So we need to think a little bit about disk structure when we're trying to understand disk chemistry. So these transition disks, maybe some of them are planet hosting disks, they might have a kind of uniquely rich observable chemistry due to the removal of dust and gas from the inner few AU. This kind of gives the stellar radiation a direct path into the kind of outer disk, I would say outer 10 AU of the disk. And we have this kind of exposed cavity wall. And this, depending on how your system is located, if you have a hot enough star and a cavity that's close enough to the star, you might have conditions that you kind of sublimate your ices just here at the very cavity wall of your disk. And that would mean that we're sublimating a lot of our materials, so a lot of oxygen-rich material hidden in the ices, water, complex organics, at tens of AU, and we could kind of observe that with ALMA, and that would be really great, because that would give us a way to kind of account for all of the elements that we're not, all of the ways the different elements can be partitioned into molecules that we can't access in this colder outer disk, because everything is frozen out. So we've been trying to build up an inventory of molecules kind of in these more warmer transition disks. It's been a little bit tricky. It's hard to get time with ALMA, so we're slowly building up an inventory. So I have 4 disks that I'll show over the next few slides. They're all nearby within 150 parsecs. They're gas-rich disks, so there's a lot of gas, mostly traced with CO. And they're around young A-type stars, so a little bit hotter. And I think that helps us a lot when we're trying to look for sublimation products, right? We need a warmer star. Our snow lines will be closer. Our snow lines will be further away, so we can kind of push out to tens of AU and look for cool molecules. So this is the dust emission from all of these objects. They all have structures. So we have rings, some weird asymmetries, multiple rings, a little hint of a spiral in this disk as well. These can be linked to planet or binary interactions. That's not too important. They're disks with interesting substructures to say. So we looked at these disks and we detect a lot of sulfur, a lot of SO. And I mentioned earlier that we don't see that molecule typically in disks. Before surveying these 4 objects, SO is detected in 1 protoplanetary disk, whereas CS, the carbon-bearing kind of pair of that molecule is seen in a dozen or so disks, right? So this oxygen-rich material has kind of been seen now in these 4 disks, which is really great. Where this is coming from the sublimation of ices, we think, around the inner disk here. A lot of these observations aren't fully resolved. It's pretty hard to do line observations at the same resolution as the dust, just because of the different sensitivities you need. But you have hints for it here with this SO in this disk here. It kind of sits around this cavity here. And this emission here from the kinematics, we can kind of tell that it's coming from the inner disk. It has a very broad line profile. So we're able to kind of find that this SO is probably coming from sublimation of ices. So it might directly come from, it's probably not directly coming from the sublimation of SO ice, but it might be coming from water ice reacting with H2S once they sublimate, and we can form SO pretty efficiently in the gas phase. So this is pretty cool. When we look to the CS that we see in these systems, you see it's immediately a little bit more patchy. It's not as pretty. It's not as bright. It's more extended spatially. In particular, if we look at the panel on the left again, you see the SO here. And once we bring in the CS, you see that it's radially further out. So what we think we're observing is kind of the change in main elemental carriers as we go across the water snow line, that kind of step function. So we go from oxygen-rich gas in the inner disk to carbon-rich gas in the outer disk, and that would be explained when you cross over the water snow line. So that's pretty cool. We can start mapping the water snow line in nearby disks around these warmer stars, and that's a pretty important location for planet formation, right? So I think that's pretty neat that we're able to do that now. On top of that, which is really fun, we detect a lot of methanol. I didn't talk too much about methanol in the introduction, but methanol is the simplest complex organic molecule that we have, and it can only form efficiently on the ices. So the gas phase methanol that we see in these observations has to kind of originate from the sublimation of ices. And that means that we're looking at temperatures of 100, 150 Kelvin, which is within the water snow line. So this gas is also another indirect tracer of the water snow line. And you see, again, we have this complex methanol coming from the inner disk in these systems. And that's, really great. Methanol is pretty fun too, because it's the simplest complex organic, but if you have it on the ices and you give it a little bit of UV irradiation, like you might experience in the disk, you can build a whole host of other complex molecules. So this is telling us that disks likely have a lot of complex material sitting on the ices that we can't typically see. And this sets the stage for kind of, hopefully, a very rich prebiotic chemistry that we can kind of link to what we see in comets or what we think could have been delivered to young terrestrial planets in the solar system. So we actually found more complexity than we thought. This is an example of IRS-48, which is a nearby disk. It has this very weird asymmetry, but you see there's methanol, which I showed on the previous slide. We also detect larger things. So this is dimethyl ether, methylformate, and ethylene oxide, which is a heterocyclic molecule, which has, it's a 3-member ring, 1 oxygen, 2 carbons. And I think if you jump up to a 5-member ring, so 4 carbons, 1 oxygen, you end up with the backbone for ribose, which is pretty cool. So this is pretty fun. We found more complexity than we thought we would. That's great. And we also found some isotopes too, which is pretty fun. So isotopes of carbon. These have been becoming pretty popular in the field of kind of in exoplanets, looking at atmospheric composition. There have been kind of proposed as a tool to unravel formation scenarios versus kind of core accretion or gravitational instability or such like that. This is an example of, I think, the first planet where they detected the 13 CO. They found a very kind of low ratio of 30, which is a factor of a few, depleted relative to what we'd expect. So it's pretty fun. We can start connecting the 13 carbon in disks to that of planets as well. On top of that, I mentioned some sulfur isotopes as well, which is pretty fun. We found 34 and 33 SO for the first time in this disk. It's very bright emission, and we can measure the isotope ratios of these molecules as well. This is important because we can link to isotopic measurements of comets, which are done pretty routinely now. So what we see is in the disk, I think we see slight differences to what is detected in comets, but it's still a little bit uncertain to tell exactly what's going on. But how isotopes are fractionated during star and planet formation is pretty important to kind of understanding the origins of all the different volatiles that we might get delivered to planets one day. So I think now I'm going to talk about one specific system in a little bit of detail to try and link what we see in the disk chemistry to some actual forming planets to make it a little bit more tangible, hopefully. So I'm going to talk about the 169142 system. So this is a nearby system around an A-type star. We have these two rings of dust, and you might hope there's a planet within this gap. That would be really nice. That would make a lot of sense because that's kind of how we could form this gap in the dust. And if you think that, you'd be right. There's been some recent work looking at different kind of new anarchival observations with the VLT. And you can see this little blob rotating in the disk. And this kind of, the colors of this emission could be attributed to kind of light scattered from kind of a dusty envelope around a few Jupiter mass planet. It's about as accurate as we can be with the mass at this stage. And this movement that you see over 4 or 5 years is consistent with the Keplerian orbit of something at about 40 AU. So that's really neat that we can actually see planets moving in disks. So we think we have, this is an image of the gas and of the dust in this disk, and we think we have a planet out here at about 40 AU, and maybe there's a planet within the inner disk as well. Let's speculate just for fun. There's a large gap. There might be a planet here, a companion. And let's try and understand what we could learn about the potential composition of the planets in this disk. So this is the CS molecule that we've detected. So this is carbon-rich gas. You can see it's tracing kind of the outer disk here around kind of this outer dust ring. We add an oxygen-rich gas. It's sitting radially further in, and it's kind of this half ring around here. The data is a little low signal to noise, so I think we have some follow-up which will show if this is really just half ring or a full ring, but you can see this radial dependence on carbon-rich gas to oxygen-rich gas as we get closer to the star. So what kind of composition could we expect these planets to be accreting? So we'd probably expect a radial gradient in elemental abundances from this initial theory of, C to O ratios and the water in the CO snow lines. So in the outer disk where we have that CS, that carbon-rich gas, we think that this planet is probably accreting material or has the ability to accrete material that has a C to O ratio of about 0.8 to 1. We don't think the disk is very cold in the outer disk. We don't think there's really a CO snow line. We don't detect any. The abundances that we see are still a little bit low to say we have very carbon enhanced gas like seen in other disks. So we think we have this kind of what almost expected C to O ratio, 0.8 to 1 in the outer disk. If there's a planet in the inner disk, so within that first dust ring, then it's going to be able to accrete a lot more cool stuff, I would say. There's going to be a lot more oxygen in the gas and a lot of sulfur, as we saw from the SO. So it could have a C to O ratio of 0.5 or lower. So we'd expect this planet to be oxygen-rich relative to this planet. And as we go radially outwards, we'd expect planets to become more and more carbon-rich. So that's kind of the simple scenario that we think about. But what was cool is what we found, or what Charles Law found, my collaborator, was he found this silicate molecule, SIS. SIS is a little bit weird. Silicon in general, we shouldn't see in the gas phase because it should primarily be locked up in refractory materials. So we see this kind of arc of SIS here that's kind of potentially launching from the region of the disk where we think the planet could be. And if you have a keen eye, you'll have seen this little blob in pink of the SO emission. So it might be that we have some local SO and SIS in the region of where the planet is. And this is not the first time we've seen some weird chemical asymmetries in disks. There's a couple of disks now. I showed these two here, HD 10546 and 169142. And where we think we might have planets or have had planets within these disks, we see these brightness asymmetries in molecules that typically trace shocks. in the ISM. So that is SO and SIS. Ideally, we'd observe something like SiO, silicon monoxide. That's kind of would be a better tracer than SIS because there's a lot more oxygen available than sulfur. But this is pretty cool. So we might be able to use chemistry to detect planets, but it also means that these disks are, the physical conditions of these disks are being changed by these giant planets, right? So if we take our little cartoon again and our planet is doing a lot of stuff, it might be heating the material around it. It might be shocking gas when it's infalling, right? So we might have the ices around the disk, or the ices in the vicinity of the planet might sublimate. So we might be able to create more water or more oxygen-rich material. We might even be sputtering refractory. So we might be breaking down actual dust grains and being able to create more refractory elements like silicates. So this is kind of throws a bit of a spanner in the works. We might not expect, depending on the size of the planet or the impact it has on the disk, and we might not expect that nice radial gradient abundances that I suggested 2 slides ago. So this is still in early days. There's a lot to figure out about exactly how planets impact the disks around them, but I think over the next few years with ALMA, we're going to start to build up a much better picture. So in terms of what we're doing next with ALMA, we're surveying more disks at moderate resolution to try and understand how many of these disks we can see this cool chemistry in. We have a program last cycle with ALMA looking at about 6 disks, and I think we're going to get a lot of cool observations from that. And we're going to try and look at disks that show a few weird molecules and dive deeper and try and understand exactly what molecular complexity that we have and compare that to, protostars and solar system objects. And also we need a deep dive and high angular resolution and follow-ups of systems that look pretty interesting. For example, 169142. We have some cool data coming, I think this cycle and last cycle from Charles, to hopefully try and see if this is a localized kind of accretion or heating shock of a planet, and I think that would be really neat if we do find that. But I thought I should add a couple slides on JWST, just to talk a little bit about what this amazing telescope is doing in my field. It's a little tangential to what I do, but I can talk about some of the great work some of my colleagues have been doing. So what JWST does is it allows us to kind of zoom into the inner disk, right? So although I've been looking at this oxygen and potentially water-rich gas with ALMA, if you're looking at typical T-Tauri stars, that snow line is going to be within 1 AU, and that's really out of reach with ALMA. So JWST gives us a window into the kind of the volatile content in the terrestrial planet forming range. And that's pretty important because if we look at this histogram of exoplanet detections versus semi-major axis, and we have the Earth, and that's where most planets are currently located. So with ALMA, we can trace the outer disk and try and understand what compositions they could have had if they formed in the outer disks and migrated inwards. But if we want to understand what the composition could be for the formation of planets in situ, and then also the formation of smaller terrestrial planets, we kind of need to be using JWST to get us to the inner disk. So it's still early days, but there's a lot of cool spectra coming out from Webb, and almost every disk is a little bit different. I think the quote that we've heard is that every disk is a snowflake. Every disk is a little bit special, and that's really nice. So what I show here are these, what I'm calling isolated disks. So these are disks nearby within a few hundred parsecs that aren't located in any kind of massive star-forming complex. And what you see on the top disk, we have a lot of water. All of these wiggles are lines. Every wiggle is a line. There's so many molecular lines, it amazes me. So all of these wiggles here are water lines, and this gas is water dominated. So we have a low C to O ratio in the inner disk of this object. If we go down a slide, this disk, over the same frequency range, it might have a few water lines, but it has a very bright CO2 and a lot of HCN. So we have this more carbon or nitrogen-rich gas. And we go to this final disk, looks completely different. I don't see any water, and it's really dominated by hydrocarbons and really weird hydrocarbons. It has long chains, aromatic rings, and that's really cool. So I think over the next couple of years, we're going to have more than 100 disks will be observed with JWST MIRI. So we're going to have an idea of the population statistics of what inner disk chemistry looks like and try and link that to the outer disk and also to environment as well. So if we look at this disk on the right, this is a different wavelength range, but this is a detection of CH3+, which is a ion, molecular cation, and this was detected towards a disk in Orion. So this is a disk that is in the vicinity of massive stars, and it's being irradiated externally by UV. And what we see here is this bright UV tracer popping out for the first time. So there's plenty to see and plenty to learn with JWST. And I have a couple little slides on water, because I think that's probably one of the molecules of interest to everyone. And JWST is great for detecting water. There are thousands of water lines, and it's really great. And I think we can now start understanding how water reservoirs differ between different types of discs. So on the left, we have a compact disk. So this is a small disk, a few AU in size, maybe 5 AU in radius, a very small disk. And this disk is either born small or it started out larger and it drifted and it became small, right? And we have this disk on the right, which is a large disk, and it has these rings and substructures. So it potentially has the formation of these dust traps, maybe due to planet formation, but they're different, right? We have a small disk and a large disk. And it looks like the small disks have a lot more water than the large disks in the inner regions. So how you can explain this is if you start with two disks that are the same size, they drift inwards. You have a compact disk where you have a lot of water coming from the outer disk, and there's nothing to stop it. The water can just drift all the way in, and that's great. In the structure disk, we have these rings, and this is going to be able to trap a lot of the dust or the icy pebbles. So the amount of material that can flow into the inner disk, because these are accretion disks, we expect things to be accreting, is going to be a lot lower. And this is kind of one of the initial trends that's being popped out that seems to be holding up, that was looked at with Spitzer and now with JWST, and it looks like there's a lot more cooler water in disks that are compact versus large. But that doesn't mean if you have a disk with structures that your inner disk is going to be completely dry or devoid of water. My final slide is really on the PDS-70 system. This is really nice work by Julia Perotti. This is a schematic of PDS-70. We have this outer dust ring. We have these two giant planets. And we have this inner disk. So based on the previous slide, you might expect that the inner disk, it wouldn't have very much water. It would be pretty poor, water poor. And I'll say that it is water poor from the observations of JWST, but water is there. These are some nice water lines detected in the inner disk. And they found this very hot water vapor, 5,800 Kelvin, in the inner disk. And it's probably not being delivered from the outer disk due to this huge gap in the disk. But what we can do is with just chemistry in the disk, you can form this water in situ at high temperatures. So we're able to make water in the inner region of a disk, even if it's potentially dry from pebble drift, which I think is really neat idea to look at. All right. So hopefully that was not too much of a whirlwind tour of disk chemistry. I'll go through my kind of summary slide now, and I'm happy to chat about and go back to any of these slides in particular if you have questions. So planets are forming in chemically rich environments that we can trace with ALMA now really well. We can zoom in on 5 to 20 AU scales and really look at differences in chemistry across the disk and not just looking at the disk as a whole. And the inner disk is pretty interesting. It's kind of the most fun part to me, is where we have the sublimation of ices. And if we go to larger stars around slightly different structure disks, we're able to kind of see this ice sublimation on tens of AU scales, and we get this window into kind of what is the full volatile reservoir available for forming planets, for comets, and use that to be able to connect to other stages of evolution in this cycle. And what's really fun is that we start to see these complex organic molecules, so this methanol and these larger molecules, and typically we don't see these in disks, and I think that's because they're hidden in the ices. So if we can generalize a little bit, it probably means that the midplane of disks are rich in complex molecules on the ices. So that's really great when we're thinking about building up complexity and putting that into comets and maybe delivering that to planets. And if we really have very nice spatially resolved observations, we can start to kind of unravel this disk-planet chemical connection kind of in real time almost, right? We can compare what we've seen in directly imaged giant planets in terms of, their carbon, oxygen, nitrogen, or sulfur abundances, but also observe directly in disks where we think we have forming planets, what material is around them and what is able to potentially be accreted. And I think isotopic ratios will be fun to help figure this out as well. I think it's still early days in terms of disks, in terms of how many kind of different isotopes we can detect and how we can understand the processing of these isotopes, but I think it's pretty cool, and we can start to do that now as well. And then finally, in the next few years, JWST is going to quickly provide a lot of really nice complementary information on the inner disk. And I think we need ALMA and JWST. We have to connect the inner disk to the outer disk. JWST is going to be great. We're going to observe, I think, I would say at least 200 disks in the next couple of years. And I think that's will be a really rich data set to look at. All right. Thank you for listening. Happy to take your questions.
Thank you so much for this amazing talk. It was really cool. So if anyone has any questions, feel free to raise your hand, and I will call out your name so you can ask your question. And please, if it's okay for you, when you're asking your question, show yourself on the video. So yeah, are there any questions? I actually have one question that's maybe a little bit more speculative, but with ALMA, we see a lot of disks that have major gaps forming out quite far away, and most of these gaps we don't know if there's a planet in there or not, but we can assume most of them will have planets in there. So does it tell us something about the planet demographics as far as we know it? Because these cold Jupiters are quite difficult to observe.
Yeah.
So
I think that all of the kind of very pretty pictures we see with ALMA are not always a typical disk. I think we've looked at the nearest and brightest and most massive disks. So we're looking at like the top 10%, I think, of disks. And they're the ones where we see a lot of these large scale substructures. We're looking at potentially giant planets on 10 to 100 AU orbits. And I think if you compare that to the population of kind of wide orbit and directly detected planets in terms of statistics, I think maybe they're a little bit similar, and they're not the most typical planet, but they're the most easily observable. But these older, colder Jupiters, I think it's harder. I think around every disk systems, we're detecting, planets on these kind of orbits. But I think once you go to more evolved, colder, yeah, I think it's a little harder. Yeah.
makes sense. Lynn?
Yeah, hi. Thank you so much for such an amazing talk. And I just figured I'd throw out a question, even though, I mean, planet formation is not my specific subject, so maybe this is a naive question or something that I assume it's something that we simply don't know yet. But even though it feels obvious that there should be differences chemically in the different disks, it's to me surprising that there's so much difference in the chemistry. This plot with like the hydrocarbons I thought was really cool. So my question is, do we know what is the main driver of the difference in chemistry? Is it just protostellar cloud? I assume this is an active research question, but is the chemistry being created in the disk, like during its lifetime, or is it just fully inherited?
So I think we have some inheritance of ices from earlier stages in star formation. So I think in particular, some of the work that I've done is we're finding these complex molecules in disks where the current conditions are too warm for us to make them on the ice. We have disks where we don't have the freeze out of CO, and we require the freeze out of CO to make some of these molecules. So I think there's some inheritance of the ices from earlier stages, but I think there will be some potentially spectral type dependence on the chemistry. There may be some environmental dependence if you have things in clusters versus there might being isolated. There's some initial wiggle room, I think, in elemental abundances. So if you're in a part of the cloud that has a little bit more carbon than oxygen, then you're going to have more carbon in your disk. And I think we haven't quite got the population statistics yet to understand that. There's some ALMA large programs going on, particularly one DECO, the disk exoplanet connection, led by Ilse Cleves. And I think they're going to look at about 100 disks with ALMA in a way that you can kind of have a better idea. 100 smaller, more typical nearby disks and have a bit better of an idea. But it might depend, for example, on if you form a planet or not in your disk. Because we know that exoplanet systems are all different, right? So we need to figure out what led to that diversity on a kind of a formation side of things, and that will impact the chemistry as well, I think. So it's a bit of
it's complicated.
Yeah.
Yeah. And I mean, if the disk creates the planet or the planet creates the disk, all of these things. And I guess it depends on like people here interested in rocky planets versus gas planet disks, I guess, if you call them that. Yeah. Thank you.
All right, Tobias.
Oh yeah, hi, thanks for the very nice talk. Maybe you've mentioned it and I've just missed it, but you mentioned this SIS that is rather expected to be locked up in the refractory material, right? What could be the explanation that it's not? Like, are there any processes as of why you would see it in the disk?
Yep. So the way to get it off the grains would be some kind of shock or some sort of kind of sputtering of the grains. And I think what was proposed in the paper is that you might have this young planet which is able to launch some sort of outflow, was one suggestion, because we have this extended emission. So it could be some sort of outflow that is shocking gas in the disk, or it could be that the planet itself, it creates these resonance spirals when it's orbiting in the disk, and these spirals can shock the disk as well and create these molecules coming off the grains. But generally it's pretty new. We're not quite sure how physical it is that we can impart that much energy into the system to create a shock like that. I think we're waiting to get the follow-up observations delivered to kind of confirm that this is exactly what we're seeing. And then we think we can take it from there, I think.
Okay, cool. Yeah, thanks.
Any further questions? Because otherwise I've got to fund it all more speculative one. So ALMA has given you a lot of really interesting results, but if you got to design your own instrument, space mission, whatever, just focused on these disks, what would you want? Like, what would be the most interesting features or things, thresholds you need to reach?
Yeah, for me, I'm interested in how much complexity we can detect. So there are some disks where we see a lot of complex molecules in the gas phase, and I'd like to look at them with a very long time and see if we can get slightly larger molecules, right? If we can maybe find a very simple sugar, something like that, that would be really fun to me, because I think at some point, once you know you have a certain level of complexity, that's enough, right? You can assume that the other processes that are happening on the dust screen, so you don't need to detect anything extremely huge in your disk. But I think if you detect some larger molecules, a few steps up, say like we have methanol, maybe ethanol would be great. Once we know we kind of have that next level of complexity, I think that would be really great. And we can really make, with that is enough to make robust comparisons to comets and protostars. So I think we just are one step away, I think, from what I think would be really cool.
But for these more complex molecules, we already know what wavelengths they will be emitting at and need to know what the exposure time should be.
Yeah, so we know where the lines are and their strength depending on how many of the molecules are there. Right now, it's just a case of estimating what the abundances should be. And what we found so far is when we find these big molecules, they're a lot more abundant than they should be. So it looks more optimistic, but we don't understand why. So relative to methanol, if you look at a protostar, some of the molecules we're finding in disks, they should be at the level of about 2 to 5%, maybe, if we're being optimistic. And if that was the case, we wouldn't have seen them in disks, because in disks we're detecting things from 20 to over 100% relative to methanol. So we're seeing a lot more complexity than we maybe should, which I think is really fun. So there are a couple ways to approach this. We have to do some, unbiased surveys that we're trying, and then some targeted observations on kind of the best next molecule to find. But the timeline is just quite slow, because we apply for ALMA once every year. And I think I'm just about to get data delivered that I got accepted. Like, I don't know, I wrote the proposal for more than 18 months ago. So it's just, it's slow, but we're trying.
You're getting there.
In that vein, for more fun speculative questions then, and maybe this isn't something that we know, but if we were gonna try and do this in a magical, eternally funded world where we get to do whatever we want, if you're able to, I don't know, like track how much methanol is in a disk over a long time. I mean, how sensitive are we though? Like by how much would that level have to change before we could even pick up on that? Just
Yeah,
ballpark,
I think the
like.
chemical timescales are gonna be on thousands of years, I think, is where it's
That's
gonna
kind of what I'm
matter,
thinking.
unless
So
I don't think it matters in terms of a
like
function
a
of time.
6-month survey, I don't know if it would like meaningfully.
I think it depends. If we're thinking that there are structures in these disks induced by planets, then it would be fun to go back after a certain amount of orbital time. That's
true.
pretty cool. But for something around a 2 solar mass star at 10 AU, the orbital time scale is like 40 years.
Yeah,
so
right.
you can do like a quarter of an orbit is realistic in the career of a
Of a
career
scientist.
of a scientist, maybe half orbit.
Yeah.
So yeah, it just is a bit of a long game, I think.
Yeah.
But the actual
inheritance tax on proposals.
Yeah, the actual kind of uniform chemistry in the disk, it shouldn't change unless it's being perturbed by a planet, I would say,
Right.
on year timescales.
Yeah.
Or you might have changes due to, say, flares from your star might irradiate, different levels of radiation on the disk and things like that. But not thinking about that, then it shouldn't change that much.
Yeah. Yeah. That's really fun to think about. Thank you.
Are there any more questions? Okay, in that case, I think we're going to call it a day for now. So Alice, once again, thank you so much for giving this talk. It's really interesting. And yeah, we will be back next month with Maggie Thompson on the 3rd of October, same time.